Right then, so last time we talked about some basic stuff about parametric curves. Okay, now that we actually know what those are, our next goal is to try to extend methods of calculus to them. So section 11, or 10.2 is calculus with parametric curves. Right then, so we're just going to be concerned with two main things today. The first is we want to talk about tangent lines to parametrically define curves. So that would be like slopes of tangent lines and also concavity. And the other thing is arc length of parametric curves. Okay, so let's just get into both of those. So, regardless of context, if we're talking about the xy plane, and y is the dependent variable and x is an independent variable, as they usually are, then every time you're talking about the slope of some curve, the slope of the tangent line to some curve, you're always talking about dy dx. Okay, regardless of context, this always means slope of the tangent line to a curve. So, in the case where you have a parametric curve, what you've got going on is x as a function of t and y as a function of t. So how do you compute dy dx? Well, it's quite simple. All you have to do is take dy dt, the derivative of y with respect to t, and divide that by dx dt. And then that will give you the slope of the tangent line, provided dx dt is not 0. If dx dt is 0, then this is undefined. Which, by the way, if the slope of the tangent line is undefined, that makes the tangent line vertical, which can happen. Okay, and then the other thing is concavity. So concavity, again, regardless of context, you're always talking about d squared y dx squared. In this context, that is going to be d dt of dy dx divided by dx dt. And of course, dy dx is right here. Okay? So, of course, we're going to do some examples. So let's see here. Suppose we want to find the slope of the tangent line to the curve and the parametric equations for this curve are x of t equals te to the t, and y of t equals t plus sine t. And let's say we're only dealing with t being non-negative. Okay. So, if you want to find the slope of the tangent line to this curve, you just need this formula. So, first of all, dx dt, also known as x prime of t, is just the derivative of x with respect to t. So, for this one, we're going to have to do a product rule to find its derivative with respect to t. So, first times the derivative of the second, plus second times the derivative of the first. So we get this, which, by the way, is the same as e to the t times t plus 1. dy dt, which again is also known as y prime of t, This is 1 plus the cosine of t. And so, by this formula, dy dx is just going to end up being e to the t times t plus 1. Oh, wait, no, it's the other way around. It's going to be 1 plus cosine t divided by e to the t times t plus 1. That's better. Okay? So that's all that's going on there. It's just a formula. And this time, it actually is as easy as it sounds to just plug it into a formula. Okay. Next up, let's say we want to find not just the slope, but actually the full equation. Not that that's much harder. Of the tangent line to the curve. This curve is root t and t squared minus 2t. And let's say at the point that corresponds to t equals 4. Well, first of all, let's just understand what that means. It's a parametrically defined curve. So that means when t equals 4, x and y will be some particular values. Specifically, x will be 2 and y will be 8. Okay? All we're asking for is what is the equation of the tangent line to this curve at that point. Again, first of all, first of all, to find the equation of a line, you're going to need the slope of the line. To find the slope of the line, you need dy dx. To find dy dx, you just need this. So, dx dt, or x prime, is just going to be 1/2 t to the negative 1/2, which by the way is the same as 1 over 2 root t. dy dt, otherwise known as y prime of t, is 2t minus 2. So, dy dt over dx dt is dy dx, and so dy dx is just going to be 2 times t minus 1 divided by 2 root t. And in case it wasn't clear what I did there, I just said the derivative of y with respect to t can be written as 2 times t minus 1 by just factoring out a 2, and then yeah, you have this, and then you can cancel the 2's and say that this is just t minus 1 over root t, which also can be written as t to the 1/2 minus t to the negative 1/2, but whatever. Okay? Now specifically, we're trying to figure out the tangent line when t equals 4. So, wait a second. I did make a mistake. Sorry about that. What I have done is I have multiplied dy dt by dx dt, which is not what you should be doing. You should be dividing dy dt by dx dt. Okay, so actually we're dividing by 1 over 2 root t. Then this actually becomes 4 root t times t minus 1. You know, that's a good enough way to write it as any. Okay, as I was saying, we're interested in where t equals 4. So, of course, we want the slope when t equals 4. So, you say dy dx evaluated at t equals 4. The bar just means evaluated at. This is going to be, well, 4 times square root of 4 times 4 minus 1. So that would be 24. 4 square root 4 times 4 minus 1. This comes out to be 24. Okay, so with that, we have the slope of the tangent line. In order to find the equation of the tangent line, you're going to need two things. You're going to need a slope and a point on the line. Or at least that would be sufficient information to find the equation of the tangent line. So we need a point on the line. Well, we're specifically looking at the point where t equals 4, so let's look at what point that would be in Cartesian coordinates. X of 4 is going to be the square root of 4, which is 2. Y of 4 is going to be 4 squared minus 2 times 4, which is 8. So the point on the curve, or the point on the tangent line that we can use is 2, 8. Specifically, this is the point of tangency. Okay, then as always, we can do the point slope form of the equation of a line and say y minus 8 is equal to 24 times x minus 2. And that is at least one form of the equation of the tangent line. Of course, there are other ways to write it. We can write it in a y equals mx plus b form by first distributing everything on the right, so we can write y minus 8 equals 24x minus 48, then add 8 to both sides and get y equals 24x minus 40. And then that's the slope-intercept form of the tangent line. Okay? So, all stuff that you've done in Calculus 1 except for, this formula. Okay? Okay, now let's look at this one. Seeing as how we can pretty much figure out everything about the tangent line of a parametric curve now, that opens up some new questions. So we can say, for example, in this one, find the points on the curve x of t equals e to the sine t, y of t equals e to the cosine t, for t being between 0 and 2 pi, where the tangent line is horizontal or vertical. Okay. Well, as always, we need to find dy dx. So, dx dt, well, this is a chain rule. This is going to be e to the sine t times cosine t. And then dy dt, that's also a chain rule. This is going to be negative e to the cosine t times sine t. Wait a second. Huh, I appear to have made a mistake in my notes. Okay, that's fine. I'll sort it out later, before I upload this video. Okay, so then dy dx is just going to end up being dy dt divided by dx dt. Yeah, I made a big mistake in my notes. Jeez. Okay. So dy dt divided by dx dt. So this becomes negative e to the cosine t times sine t divided by e to the sine t times cosine t. Okay. Right, well, we can leave it like that. Like it doesn't get a lot nicer than that. But I suppose you can also write it as negative e to the cosine t minus sine t times tangent t. Same thing. Anyway, to find where this is horizontal, to find where the tangent line is horizontal, we need to find where dy dx is 0, as always. So, we say 0 equals negative e to the cosine t minus sine t times tangent t. Well, e to any power is positive. It can never be 0, right? You can't raise e to a power and get 0 out of that. So, if it's positive, then that means we can divide both sides by it. And that gives us just that 0 equals tangent t. Okay, this occurs at infinitely many locations, but we're specifically interested in the ones that are between 0 and 2 pi. So, tangent of t will be 0 whenever sine of t is 0, because tangent is sine over cosine. Sine is 0 exactly at 0 and pi. And those are the locations, well, no, I should say those are the values of the parameter t at which the tangent line is horizontal. Okay? Now, if you want to find the actual point, which is what this problem is asking for, then you actually have to plug these values of t into the curve. And that's fine, that's not hard. All you have to do is say x of 0. X of 0 is going to be e to the 0, which is 1. Y of 0, this is going to be e to the 1, which is e. Meanwhile, we also need to look at x of pi and y of pi. So, let's see, x of pi is going to be e to the 0, which is 1. And y of pi is going to be e to the negative 1, which is also known as 1 over e. Okay? So what we get here is that we have a horizontal tangent line at the points 1e and also 1 over e. Okay, so that's the first part. Next up, we want to find where it is vertical. What's weird here is that I made a mistake earlier on in my notes, but then it turned out that it gave me the correct answer for this problem. Whatever. Right, so to find where the tangent line is vertical, well, the tangent line is vertical exactly when its slope is undefined. So what we're looking for in that case is for this function right here to be undefined. All right, well, easiest way to see where this is undefined is to set this denominator equal to 0. Because obviously if the denominator is 0, then the fraction doesn't make sense, right? So, maybe I'll just continue over here. So to find whether the tangent line is vertical, we just need to say e to the sine t times cosine t has to be equal to 0. Now once again, e to the sine t could be a lot of different numbers, but whatever they are going to be positive. You can't get e to something and get 0 out of that. You can't get e to something and get negative out of that. So we can divide both sides by e to the sine t, which means cosine t has to be 0. That too is a equation with infinitely many solutions, but specifically we're just concerned with the ones between 0 and 2 pi. So between 0 and 2 pi, cosine t is 0 at exactly pi over 2 and 3 pi over 2. Okay? So then next up, again, we have the parameter values at which the tangent line is vertical, but we need to actually put them into the curve in order to figure out what those specific points are. So let's look at x of pi over 2. X of pi over 2 is going to be e to the sine of pi over 2, which is e. Y of pi over 2 is going to be e to the cosine of pi over 2, which is e to the 0, which is 1. Similarly, we need to look at x of 3 pi over 2. X of 3 pi over 2 gives us e to the sine of 3 pi over 2, which is e to the negative 1, in other words, 1 over e. And y of 3 pi over 2, this is going to be e to the cosine of 3 pi over 2, which is e to the 0, which is 1. So we have vertical tangent lines at the points E1 and 1 over E1. At those 2 points, we have vertical tangent lines. At these 2 points, we have horizontal tangent lines. Okay. Okay, now this next one is going to be a little weird. At first it will look easier, but I assure you it will be weird. So, once again, directions are the same. We want to find the points in the curve where the tangent is horizontal or vertical, but it's a different curve, of course. So x is going to be t cubed minus 3t. Y is going to be t cubed minus 3t squared. And no restrictions on t. You can just vary over all real values. Okay. So again, we're asked to find where the tangent line is horizontal or vertical. That means we're going to need dy dx, which means we're going to need dx dt and dy dt. So, dx dt, that's going to be 3t squared minus 3 dy dt is going to be 3t squared minus 6t. And then, if you want the slope of the tangent line, dy dx, now you're talking about 3t squared minus 6t divided by 3t squared minus 3. And this, by the way, can be written as t squared minus 2t divided by t squared minus 1. Okay. So, in order to get the tangent line to be horizontal, we just need this to be 0. Okay. So let's see, if you set this to 0, So 0 equals t squared minus 2t over t squared minus 1. The only way that fraction can be 0 is if its numerator is 0. No matter what its denominator is, well, that's not going to matter. Okay, so this is the same as saying 0 equals t squared minus 2t, which is the same as 0 equals t times t minus 2, which is the same as t equals 0, or t equals 2. Okay, and then, as before, if we put these points into the curve, let's see, x of 0 is going to be 0 cubed minus 3 times 0, which is 0. Y of 0 is going to be 0 cubed minus 3 times 0 squared, which is 0. Then let's check out t equals 2. X of 2 is going to be 2 cubed minus 3 times 2, which is 2. Y of 2 is going to be 2 cubed minus 3 times 2 squared, which is negative 4. Okay, so that means that we have a horizontal tangent line at the points 0, 0, and 2, negative 4. Okay, now let's talk about where we have a vertical tangent line. So a vertical tangent line would occur whenever the denominator is 0, right? So, because, that's the only way that this dy dx could be undefined, right? So we're saying t squared minus 1 equals 0. Of course, that's the same as saying t minus 1 times t plus 1 equals 0, which means either t equals 1 or t equals negative 1. Okay. So then you take x of 1 and y of 1. Let's see, x of 1 is going to be 1 cubed minus 3 times 1, which is negative 2. Y of 1 is going to be 1 cubed minus 3 times 1 squared, which is negative 2. Yes, I don't know why it took me that long. Okay, and then x of 1, or negative 1 actually. This is going to be negative 1 cubed plus 3, so that ends up being 2. And y of negative 1, you take negative 1 cubed minus 3, that makes negative 4. Okay, so that means we have vertical tangent lines at the points negative 2, negative 2, and 2, negative 4. You see a problem with that? The truth is that there is no problem with this, but it sure looks like it, doesn't it? It sure looks like it's saying that we have both a horizontal tangent line at 2, negative 4, and also a vertical tangent line at 2, negative 4. And it is. And that sounds impossible, right? But it's not. It's not impossible because if you look at the actual graph of this curve, well, I've given you an actual diagram in my notes, but approximately, it looks something like this. Okay, and it so happens that this point right here is 2, negative 4. So what's going on here, you see, is that the first time it crosses through 2, negative 4, is when t is -1. And at that point, it's going up like this. So we have a vertical tangent line. Then it comes around, and it hits 2, -4 once again when t equals 2. And then it has a horizontal tangent line. Okay? So this can certainly happen. It's a little weird, but this could certainly happen. Okay. So then there's the matter of concavity, which isn't much harder. Again, it's just plugging stuff into a formula. It's a different formula, but you know, whatever. So what we are asking for here is for which values of t is the curve x of t equals t cubed plus 1, y of t equals t squared minus t, concave upward. So this question means the same thing that it would have meant in Calculus 1, it's just now you're dealing with a curve that you wouldn't have dealt with in Calculus 1. We're just asking at which values of t is the curve doing this kind of thing, as opposed to this kind of thing, curving upward instead of downward. Okay. Well, in order to figure that out, we're going to need d squared y dx squared. And in order to get d squared y dx squared, we're going to need dy dx, which is here. So, dx dt, that's going to end up being 3t squared. dy dt is going to be 2t minus 1. This means that dy dx is just going to be dy dt over dx dt, which is 2t minus 1 over 3t squared. Okay. Then, according to this formula, we need to take the derivative of this with respect to t, and then divide that by dx dt. Okay? Well, let's see here. So, derivative with respect to t of dy dx, that's a quotient rule. Okay, so this one is, well, okay, actually, I guess you can get out of doing it by the quotient rule. Yeah, why don't we actually do that? Yeah, we can say that this is 2/3 t to the -1 minus 1/3 t to the -2, and then if you do it like that, then you don't have to use the quotient rule, you can just use the power rule. Okay, yeah, fine. So then, if you take the derivative of this with respect to t, you get -2/3 t to the -2 plus 2/3 t to the -3, and that's the derivative with respect to t. Let me just make 100% sure that that matches up with what I have in my notes. I think it does. If it doesn't, I'll edit this out. Okay. So now we just need to take this and divide it by dx dt. So we just take this and divide it by dx dt, that's 3t squared. And this ends up being d squared y dx squared. Okay, great. So, now we desire to know where this is concave upward. It's concave upward exactly when d squared y dx squared is positive. Okay? So what we're asking for is, where is this greater than 0? And there's a couple of ways that you can do that. The way that I did it in my notes is similar to how you did it in Calculus 1, where you first found where it was equal to 0, and then you just make a number line saying, this is the only place where it's equal to 0, so I just need to check either side of that. You can also just say, well, this is, finding where this is positive is just solving the inequality. This is greater than 0. Now, as it is, 3t squared is always positive. So that means that if you multiply it by both sides, you don't have to switch the sign of the inequality. So this can be rewritten as negative 2/3 t to the negative 2 plus 2/3 t to the negative 3 is greater than 0. All right. This can be rewritten as, let's see here, I guess 2/3 times 1 over t cubed minus 1 over t squared. So we're asking, where's that greater than 0? All right, well, 2/3 again is positive, so we can divide it by both sides with no harm done. And then we can add 1 over t squared to both sides. So then this can become 1 over t cubed has to be greater than 1 over t squared. T squared is positive, which means that you can multiply it by both sides without flipping the sign of the inequality. So then this can become just t squared over t cubed has to be greater than 1. Now, t squared over t cubed, we happen to know that that is 1 over t. Okay? So in other words, we're looking to see where 1 over t is greater than 1. 1 over t will be greater than 1 only when t is less than 1. Actually, it's got to be less than 1 and greater than 0. Because, I mean, if it's less than, well, if it's equal to 0, then obviously this doesn't make any sense at all. If it's less than 0, then this is negative, and so then that's not greater than 1. And if t is greater than 1, then 1 over t is less than 1. So, on that interval, it is concave upward. For that interval for t. And of course, this can also be written as the open interval from 0 to 1. Yeah, so again, this is just one way of doing it. I did in my notes a slightly different way. Gets you the same answer. Okay. So that's about all that we'll be concerned with for the tangent line to a parametric curve. And there's just one more thing that we should discuss for today, and that's the arc length of a parametric curve. The arc length of a parametric curve is the integral from alpha to beta, where alpha and beta are the two bounds for t, of the square root of dx dt squared plus dy dt squared dt. And by the way, I just want to point out that you can derive the formula for arc length that we had before in section 8.1 from this, because you can parametrically describe a function as x equals t and y equals that function of t. And then when you put it into that formula, you'll get the formula that we had in 8.1. Anyway, there's not a lot to say about this, so let's just do some examples. So we're going to find the exact length of, let's see here, x of t equals e to the t minus t, y of t equals 4e to the t over 2, and we're going to say t is between 0 and 2. Okay, well, we have a formula for that. We just need to take the integral from 0 to 2 of, the square root of dx dt squared plus dy dt squared. So dx dt this is going to be e to the t minus 1. dy dt, this is a chain rule. This is going to be 4e to the t over 2 times 1/2, which just comes out to be 2e to the t over 2. And then you just put it into this formula. So our arc length will be the integral from 0 to 2 of the square root of e to the t minus 1 squared plus 2e to the t over 2 squared dt. So you square these, this becomes integral from 0 to 2 of the square root of e to the 2t minus 2e to the t plus 1 plus 4e to the t. Right, because when you take e to the t over 2 and you square it, you multiply the exponents. So t over 2 times 2 is just t. You combine some like terms here, and this becomes integral from 0 to 2 of square root of e to the 2t plus 2e to the t plus 1 dt. So now you have to do that integral. And it's the return of the weird factoring, because this is a quadratic in e to the t, right? This is e to the t plus 1 squared. So this is the integral from 0 to 2 of the square root of e to the t plus 1 squared dt. And then it so happens that from 0 to 2, e to the t plus 1 is positive. Actually, it's always positive, so I guess it doesn't matter much. In any case, we don't need to worry about absolute values, so then this just becomes integral from 0 to 2 of e to the t plus 1 dt. We do that antiderivative, it just becomes e to the t plus 2 plus t, evaluated from 0 to 2. This becomes e squared plus 2 minus e to the 0 is 1. And so what we get here is e squared minus 1. And that's our arc length. Just kidding. 2 minus 1 is in fact 1, not negative 1. So yes, this should be plus 1. Sorry about that. That's why you need to make notes for yourself when you're giving a lecture. It's because if you don't, then you'll never know if you made a mistake. In fact, even if you have notes, you might not know if you made a mistake or not. Okay. And let's do one more. So once again, we're going to find the exact length of the curve. This one is going to be a bit more complicated. Cosine t plus the natural log of tangent of 1/2 t, and y of t is just going to be sine t. And let's see, the values for the parameters are from pi over 6 to pi over 3. Okay, so once again, we just need to put it into this formula, but again, that's not as easy as it sounds. For the previous problem, finding the slope of the tangent line, then it was as easy as it sounds, but now I don't think so. So dx dt, okay, derivative of this thing with respect to t, I guess that would be negative sine t plus, okay, that's a chain rule, so 1 over tangent of 1 over 2t, sorry, times secant squared of 1 over 2t times 1/2. Two applications of the chain rule. And then we're going to want to simplify this a bit because we're going to eventually plug it into a formula, so we don't want it to be messy. So this is negative sine t plus, let's see here, 1 over 2. Okay, secant squared is the same as 1 over cosine squared. And tangent is sine over cosine. So sine over cosine times cosine squared gives us sine cosine. So 2 sine of 1/2 t cosine 1/2 t. And that's all on bottom. Okay. And then you might notice that this is a thing. This is this takes the form of the double angle formula for sine. Sine 2 theta is 2 sine theta cosine theta. Okay? So this is actually equal to negative sine t plus 1 over sine 2t. Wait, no, sine t, sorry. Let me explain what that is. The sine of 2 theta is 2 sine theta cosine theta, right? Make theta equal to 1/2 t, and then that's what's happening here. And by the way, this is the same as cosecant t minus sine t. So that's dx dt. All right, next up is dy dt. dy dt is cosine t. Okay, so now we just need to put them into our formula. So arc length is going to be the integral from pi over 6 up to pi over 3 of the square root of that squared. So let's see here, cosecant t minus sine t squared plus cosine squared t dt. Okay, so you're going to have to distribute that. integral from pi over 6 to pi over 3, square root of cosecant squared t minus, okay, cosecant times sine is just 1. So then minus 1 makes minus 2. Then add to this sine squared t plus cosine squared t is still around, dt. Okay, now sine squared plus cosine squared is 1. 1 minus 2 is negative 1. So this becomes integral from pi over 6 to pi over 3 square root of cosecant squared t minus 1. It so happens that cosecant squared t minus 1 is cotangent squared t. So then this becomes integral from pi over 6 up to pi over 3 of the square root of cotangent squared t dt. Now, from pi over 6 to pi over 3, cotangent is positive. And I'm going to confess that I adapted this problem from a very similar problem in the book, but the bounds for t were different. Over those bounds, the cotangent wasn't always positive, and so then you have to take the absolute value. But in this case, you don't have to. In this case, the square cleanly cancel. So this just becomes integral from pi over 6 up to pi over 3 of cotangent t dt. Right then. Do you know how to do that antiderivative? Here's how you do it. We can write this as integral from pi over 6 to pi over 3 of cosine t divided by sine t dt. When you do that, you can do a u substitution. Okay? I'm going to erase this just because we don't need it anymore. If you set u to be sine t, then du becomes cosine t dt. And I guess while we're at it, we better change the bounds as well. Let's see, when t equals pi over 6, u is going to be the sine of pi over 6, which is 1/2. And when t equals pi over 3, u is going to be the sine of pi over 3, which is the square root of 3 over 2. So this becomes integral from 1/2 up to square root of 3 over 2, 1 over u du. This is just natural log absolute value of u evaluated from 1/2 up to root 3 over 2, which is the same as natural log of root 3 over 2 minus natural log of 1/2. And that's fine. That's a good enough answer for me if you're writing this on like a quiz or a test. You can write it other ways. You can write this as the natural log of root 3, because log has the property that when you subtract them, it's the same as dividing their arguments. So root 3 over 2 divided by 1/2 is just root 3. And then that, by the way, is natural log of 3 raised to the 1/2. And log also has the property that when you have an exponent in the argument, you can just take that down into a coefficient. So this can become 1/2 natural log of 3. Well, not really the point. The point is that any of those will work as the arc length of this curve. Okay. So other than the arc length, which I recognize as new, it's at least as new as 8.1, this is all stuff that you've mostly done in Calculus 1, just applied to a different context. Okay? And if and when you take Calculus 3, you'll find that that's going to happen a lot. Okay? So homework is up. Go ahead and get some practice with that.